Hello everyone and welcome to ENGEN102 21B Workshop 11, and we're dealing with statistics again. Now statistics are just one of those things you're going to have to get used to. I mean, in physics there's a thing called statistical physics which nobody likes, but we've come to accept that it is reality. And talking of physics, I'd like to mention an experiment I did a while ago. This was a speed of light experiment. I had a laser, I shone it supposedly over a distance, boom, 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 and I was trying to measure the speed of light. And I was sending out a modulated signal, and as it came back, the signal was going to be slightly out of phase. And by the amount it was out of phase, I could tell the distance, and so V is equal to change in D over change in t. So I can work out the velocity of the speed of light if I know how far it is and how long it takes. So I did this experiment. I was supposedly accurate to within 1%. And I worked out the speed of light was 5 times 10 to the 8 meters per second, plus or minus 5 times 10 to the 8 meters per second, to 1 standard deviation. So according to my research, there was a 16% chance that light was actually going backwards. Now, all I could really make from that conclusion was that A, the speed of light was finite, and B, we should use some better equipment next year. And next year, when they offered the same experiment, they had better equipment. So anyway, to most people, something like that, 2 is a number, but to me, this is a number. So it's got an amount, it's got an accuracy, and it's got a reliability. And you're probably wondering, how does this actually apply to you as engineers when you're building stuff? And that's partly because whenever we measure stuff, for example, there's always an uncertainty. So if I grab a ruler and it's got all these little things, sometimes the things I'm going to measure are going to end up between there. So what's the most accurate that you can measure with a ruler? And it's usually plus or minus half a mil. And this measurement of anything that you're dealing with becomes quite important, especially when you add in things like expansion and contraction of systems. And this partly goes into your safety factor. Now, there is something called the Heisenberg uncertainty principle, Heisenberg, and basically it says that your change in momentum and your times your change in position, change in x is going to be greater than or equal to some constant, which leads, of course, to the joke about how Heisenberg has been driving down the highway and he got pulled over by a traffic officer, and the traffic officer goes, "Do you know how fast you're going?" And he goes, "No, but I know exactly where I am." But anyway, normally this is so small it actually only applies down at the atomic level, but occasionally it does pop up into the macro level, back into the size of the real. But basically this says that there is a fundamental limit on how accurately we can measure anything. And that means at that point, we're going to get uncertainties. And so it's good to know how to deal with these uncertainties. And as I was saying in the last lecture, there's 2 types of uncertainties. There's uncertainties which are independent. So independent. And these are things like if you're playing i.e. dice or whatever. Every time you throw a dice, it's a totally random chance it'll turn up as anything. And they're surprisingly enough dependent or systematic. Dependent And this depends upon the previous uncertainty, which depends upon the previous uncertainty, which, so say you're playing snooker and you hit the ball and that goes off and hits a cushion and that goes off. The speed and velocity it is here depends upon uncertainty here, uncertainty measurements here, and uncertainty measurements with actually hitting the ball. So these become cascading uncertainties. And uncertainties. It does get to the ridiculous point now where you get architects say, make a wall 100 meters. Hopefully you can see what the problem with defining a wall is. 100 meters long plus or minus 1 millimeter. And it's quite simple. If this warms up, the wall's going to expand. If it gets cold, it shrinks. But you still get people designing stuff like this. But it also turns up if you're engineering, like the classic one is if you're designing a Formula One car, you got your cylinder, and then you got your piston. These are made out of different metals. When they cool down, they contract at different rates. And in fact, the Formula One car now, when it is cold, it is effectively seized. And we use tricks like that all the time in engineering. If you want to fit stuff, I mean, they've done this for hundreds of years. If you want to fit something like an iron tire onto a wooden horse carriage, so say, or onto a wheel, a wooden spoke wheel, what you do is you heat up the steel expands, you cool it, and then it contracts down. Oh, okay, that's beside the point. But uncertainties, everything that you are going to deal with, at every single measurement, there is going to be an uncertainty. Like I was designing a board and 3D printing it the other day, and I was printing these holes as 1.8 mils. But in actuality, due to the processing, they actually ended up as about 1.5. Grr. So everything you do will have uncertainty. We will try and ignore this and pretend this. And the normal way that we get around uncertainties is something called a safety factor. So when you build stuff, you know, like a car or something, you might design a 3-to-1 in the suspension system, or you might design a bridge with a 2-to-1, which means it's twice as strong as it needs to be. If you're setting up an unmanned rocket or an uncrewed rocket, it's 1.5, 1.25. If you're setting up an uncrewed rocket, it's 1.25 to 1. If you're setting up a crewed rocket, it's 1.5 to 1. That means an uncrewed rocket like a Falcon X or whatever, a Falcon Heavy, there's 25% more material in there than is required, which means that you have to have really good quality control. And the way we achieve quality control is often through using statistics. Because remember, when we're talking independent events, we end up with a bell curve. Okay, you do actually sometimes get skewed bell curves, believe it or not, but pretend that's symmetrical. We take measurements, we work out a range, we say this amount is acceptable, and we try and build everything in that range. So, you know, you got more statistic stuff to do. So you're not going to escape statistics. It doesn't matter what thing you're going to be doing. The thing is, yeah, you try not to rely on stats if you can help it, but these curve distributions and things are just you're going to get used to them. But when you buy stuff, you're going to buy, you know, diameter equals 22 millimeter plus or minus 0.1 mil. Normally we do stuff to 2 standard deviations, so that means 95% of your sample is going to be within that range. Okay, well, anyway, good luck. We're just about at the end of this course, so you've got an exam coming up, so I'll do a little bit on doing exams, especially online next week, hopefully. yeah, just have fun with your math and especially with your engineering. Good luck.